Geometry students, chapter 7 in our geometry book is all about right triangles. So we are going to go pretty quickly through this chapter because the first lesson is a squared plus b squared equals c squared in a right triangle. You know that better as the Pythagorean theorem, and it says if you have a right triangle where a and b are the adjacent legs of the right angle and c is the side opposite the right angle, also known as the hypotenuse, then a squared plus b squared equals c squared. Lesson 2 is if you have a triangle such that the three sides are in a relationship that if you took the sum of the squares of the smaller side, it would equal the square of the third side, then you have a right triangle. So the first two lessons are pretty easy. It just basically says, for all right triangles, this is true. For any triangle where this is true, then we know it's a right triangle where the side opposite C is a right angle. So we're not going to do too much in those two lessons. There will be some brief classwork tomorrow for you to practice the Pythagorean theorem because we always like to practice the Pythagorean theorem, especially when we get things like the square root of 50. And we simplify that to 25 times 2 inside the radical, so we know the answer is 5 root 2. But what I'm more excited about in this unit is the third lesson, because the third lesson says if you have a right triangle and from the right angle you draw an altitude to the hypotenuse, then you create three triangles, all of which are similar. And if you're thinking, wait, that looks familiar, well, that problem is something we've looked at a lot in the similar triangle chapter. So take a look at this theorem. It says if an altitude is drawn to the hypotenuse of a right triangle, in this case CD, then the two triangles formed are similar to the original. And that means all three triangles are similar to each other. You've seen this, we've done this, this was a test question. More importantly, we can get them here in the right ratio and talks about all of these triangles here. So you've got the big one, ABC, you've got the small one, the smaller one, ADC, and then you have the smallest one, CDB. Notice how they put these triangles in order. I like coming through and saying like, okay, I'm going to put, we've got angle A, we've got angle A, we've got angle A, we've got angle B, we've got angle B, we've got angle B, and we have the right angle. So, and I think I put those all in the right spot. Good. So if we look here, angle B similar to, or congruent to angle B, right angle congruent to right angle, so those are similar. Angle A congruent to angle A, right angle congruent to right angle, those two triangles are similar. A plus 90 has to equal A plus 90, third angle theorem. This is the same as B. Over here we have B congruent to B, 90 congruent to 90, so third angle theorem. This is the same as angle A. So we know that all these triangles are congruent, and then I really like how they have the colors here. So take a look at AC. I'm going to call that little b because it's opposite angle B. I'm going to call this side little a, and I'm going to call this C. Then here, I know this green side, I know this is B. All right, and then here I know this blue side, I know this is A. And now I'm going to put some other sides in here. I'm going to call this altitude X. Okay, so if I put in X here, so we'll use a different color. So here's X. Oh, sorry, that's not X. X is here, it's the altitude. Good, it's that side right there. Now look at what we end up getting in these relationships. You've seen this before, but we'll see it again. A is to C, right? Do you see that? A is to C what X is to B. Let's take a look at that. Or let's do this one. A is to, do I have all these written correctly? Yeah, let me put in a couple more terms. I'll call this Y and I'll call this Z. So C here is X plus, or sorry, Y plus Z. This side here, AD, that's Y, and this side here, BD, is Z. So take a look at some of the relationships we can write. We can write that, let me change my marker here. A is to Z what y plus Z is to A. A is to Z what y plus Z is to A. If you look closely at that, that means that A is the geometric mean of Z and the entire hypotenuse. Another thing we could say, B is to Y what Y plus Z is to B. B is to Y what Y plus Z is to B. That means that B, which is over here, is the geometric mean of Y and the entire hypotenuse. And then lastly, take a look at these two triangles. X is to Z what Y is to X. X is to Z what Y is to X. That means X is the geometric mean of these two pieces. So that is formalized in the following two theorems, where it talks about how the altitude is the geometric mean of the two segments that it divides in the hypotenuse, and that the legs are the geometric mean of the side of the hypotenuse closest to the leg and the entire hypotenuse. So AC is the geometric mean of the entire hypotenuse and AD. CB is the geometric mean of DB and AD. Those theorems are just simple applications of these three similar triangles. We just have to remember that definition of geometric mean, which says X is the geometric mean if A is to X what X is to B. And remember, a geometric mean is X is equal to the square root of A times B. So look what we can do in this problem here. We can actually solve for a lot of pieces here relatively quickly. So if I call this X and I call this Z, we can solve for X, Y, and Z, and I'll call this 6. Let's solve for Y first. 3 is to Y what Y is to 9, because Y is the geometric mean of 3 and 9. So this gives us Y squared equals 27, so Y is equal to the square root of 27, and a better answer is 3 root 3. Alright, so this is equal to 3 root 3. Good. The problem I made up in here. X is the geometric mean of 3 and 6. So 3 is to X what X is to 6. That means that X squared is equal to 18. So X is equal to the square root of 18, or better yet, 3 root 2. So this side right in here is 3 root 2. And then lastly, Z is the geometric mean of 6 and 9. So 6 is to Z what Z is to 9. That tells us Z squared is equal to 54. And Z squared equaling 54, 9 is 3 times 3, so I can easily get that Z is equal to the square root of 54, which is equal to 3 root 6. Good? So you're able to solve for these sides of a right triangle pretty quickly if you know this is an altitude. Do not make the mistake of thinking this is a 45-degree angle and this is a 45-degree angle. It's easy to prove that these angles aren't congruent because of the other sides that they're opposite and things like that. All right, everybody. I hope you have a wonderful day. And thanks for watching the video. Tomorrow, while all the students who have algebra in their class name, you'll be doing some classwork, which I will post early for the Algebra 2 kids. All right, peace.